We begin our look at extension 2 integration basically by starting off with just some strategies. So before we look at any of the actual techniques and what have you, we're going to talk about the strategy of approaching integration. The first one, look for an obvious solution. Okay, so I mean, it might sound silly, but you know, they're not all hard. Some of them will be easy, and you look at it, oh, there's an obvious solution. So try to find some function in the integrand. By the way, a bit of English here for you. Integrand is what you integrate. So the thing after the integral symbol, that's the integrand. You then integrate it and get a primitive function. Okay. Because if you've got that, then you can set up, you know, derivative times function, that sort of idea. So we see something like this, and straight away, I hope you spot it. We've got x squared in the bottom, we've got x on the top, and I know the derivative of x squared, or rather minus x squared, probably more importantly, is minus 2x. So I can create the derivative on top, balance it out, minus a half out the front, and I see, I don't write it down. I mean, you could do it by substitution if you wanted to, but what I'm actually seeing there is du on root u. Now, du on root u is always 2 root u. It's one of these ones that crops up a lot. It's not on the reference sheet, but it's certainly worth remembering because, as I say, it comes up a lot. So if I know that's 2 root u, this becomes minus a half times 2 is minus 1, root u, and u was 1 minus x squared. Bing, there's the answer. So the obvious solution. If I can't see an obvious solution, then the next thing is to try and manipulate it into a standard integral. So the standard integrals, the whole reason we have them is to save time. I've mentioned to you, or some of you, might not have been everyone, but my first year at uni we were given a calculus textbook. It was about that thick, but in the back of it there was something like 500 standard integrals, which obviously helps solving problems because you didn't have to worry about integrating certain functions. You could just, oh righto, that's the answer. So they're there to save time. So once you've got it into a standard form, you just look at the standard integral and go, righto, that's the primitive function, away we go. Integral of e to the x plus e to the x. So the power is x plus e to the x. How on earth do we manipulate this one? Well, I use my index laws. I'll rewrite it as e to the x times e to the power of e to the x. Now, I don't know if you've spotted it yet, but we've basically got that now. Derivative times e to the function x, because the derivative of e to the x is e to the x. So that is just e to the power of e to the power of x is the answer. How about this one? So we look at this. Look, when I spot something like that, what do I see? I see x is the power on the bottom, x on 2 on top. So in other words, the bottom one is the top one squared. So now I'm starting to think inverse trig, that sort of thing. Can I manipulate it into that? So that's what I'm going to end up using, derivative over a squared plus function x squared. All right, well, if I'm going to do that, the function must be e to the x on 2. I'm going to pull the 3 out as a common factor there, so I don't have to worry about it. I'll just pull it out. It's much easier, I think. So I've got e to the power of x on 2 squared. So I now know that's the function. Therefore, I want the derivative on top. So the top would be a half e to the x on 2. Of course, I can't change the question, so to balance it, I'm going to need 4 out the front. Now I've got it in the form, so I can go, all right, 4 over 3, we've got to keep that out there. A turns out to be the square root of 2. So 1 over a inverse tan of the function over a. E to the x on 2 over the square root of 2. And just tidying that multiplication up, there's our answer. So then, if those ideas aren't working, simplify the integrand, if possible. Now what do we mean, simplify it? Bit of algebraic manipulation, or maybe trig identities, can change it and to make something a little bit easier. So you see tan theta on sec squared theta. I'm going to use trig identities. See, you look at it and you go, damn, shame it's not the other way around, because of course sec squared is the derivative of tan, but it's not much use for me having the derivative on the bottom of the fraction there. But what I'm going to do is go right back and say, well, let's just change everything to sine on cos. Let's see what happens. So I get sine on cos times cos squared. At sine theta cos theta, which I know is a half of sine 2 theta. Now I got something that's fairly simple to integrate. So we know this one's minus a quarter cos 2 theta. Okay, so that's using the trig identities. The algebra one, you want to create the derivative out front. Now the problem is the derivative is minus 2x and I've got x cubed. It's not like I can divide by x squared here. So we do a little bit of a manipulation. You see, when we factorise, it doesn't just have to be the derivative I have out the front. I could also have a multiple of the function itself out the front. In this case, 4 minus x squared. So I rewrite it like that. Follow it through. That is x cubed. So minus 4x plus x cubed plus 4x. It is indeed x cubed. But now I can split that into two things. And both of those now, I can say I've got the derivative, although I've got to play around with them a bit. I've got some multiple of the derivative times a function to a power. I can integrate it. So when I integrate it, the first one becomes a half of 2/5 4 minus x squared to the power of 5 on 2. The second one becomes minus 2 times 2/3 4 minus x squared to the 3 on 2. Obviously a mere mortal answer. There we go. Super mathematicians would write it something like that. Not always quick to spot those ones, but essentially you're trying to create a factor out the front, which is a factor of the derivative and or the function itself. That's what you're trying to use there. We classify the integrand according to its form. So if it's a rational function, then polynomial division, and we'll use the technique which we'll see later on in this topic of partial fractions. Trig functions, look at the power of the trig function. That'll determine which technique we're going to use to go and integrate it. And thanks for that. Mixture of function types, try integration by parts. But again, some of these techniques we will look at in this topic. Essentially, there's only two methods: substitution or integration by parts. That's pretty much it. Yes, sometimes we have to manipulate it to get to a point where we can do that, but everything is either substitution or integration by parts. Okay, so the first bit's just playing with some techniques of integration.